Hi everybody, welcome to another video in Trigonometry, section 5.1, verifying identities. So this section is nothing new. All the identities here we should know already, but this section we learn how to prove new identities based on the identities that we know. Right. So just a quick review. Reciprocal identity, quotient, and Pythagorean identities, all of those can be deduced from this hexagon. So tangent, where we have for a hexagon where we put a trig function on the top like tangent, there will be 3 ratio that we have. So tangent is sine over cosine, 1 over cotangent, and secant over cosecant. And of course you can rotate the hexagon. So whatever function on the top, we will have 3 ratio like that. And of course, that will take care of those 2 identities. And then the Pythagorean identity, 1 square plus tangent square equal to secant square, cosine square plus sine square equal to 1 square, cotangent square plus 1 square is cosecant square. And of course, that's what we have. Right. But in this section, we just need to emphasize on tangent is sine over cosine, cotangent is cosine over sine. So I will circle the important function. Cosecant is 1 over sine, and secant is 1 over cosine. So what did I do here is that when we use those identities, we can write any trig function in terms of only sine and cosine. So the idea here is it will be easier if you're not familiar with all of this. The first time we learn about proof identities, it will be easier if we change everything to sine and cosine. So in that case, we focus on those 4 identities. This in the previous section, we know that cosine and secant are even. And by even, we mean cosine of a negative is the same as cosine of a positive argument. So whether it is negative or not, it doesn't matter. And then the other 4 functions are odd. These 4 functions are odd. Right. Now, next we're going to prove identities. Because this is just a guideline. There's not really a unique way to prove any problem. But the way we do that, usually we start with the more complicated side and simplify to the other side, or we convert both sides to the equivalent expression, or manipulate the equation to something easier to prove. So those rather obvious, but because when we go to a particular problem, you will see there's a few ways, that more than a few ways we can do. Right, and the technique, we will look at the final the expression that we need to prove, and then we go from there. We'll try to go to there, and of course depends on the problem, we have to come up with the way to do that. Of course, like there's no one method that can prove anything. Right. So let's look at the first example. Of course, we assume that we know all of these identities, because we're going to use that and prove some new identities. Right. For example, let's prove or verify the following. If we have cosecant square minus 1 over cotangent equal to cotangent x. Now, since we have cotangent square plus 1 is cosecant square, so we have cosecant square is equal to cotangent square plus 1. If we substitute that into here, that gives us cotangent square plus 1 minus 1 over cotangent x. And because if we not get straight directly to that, 1 minus 1 cancel out, we have cotangent square over cotangent, and that cancel out equal to cotangent of x. And once, if I did not mention before, which I think I did many times, when we write a function, for example, when we write like that, we mean sine x square, like that, and not this is different than sine of x square. And this is not equal to, right? So the square into the function, meaning we take the trig function first and then we square. Because of that, we can cancel out. By that I mean we can cancel out like cotangent square and then cotangent, cancel one of them, right? And that's what we have. So usually the proof like this is more elegant. Like the more traditional way is we go from a more complicated sign, that more complicated, and go to the simpler sign. Now let's look at a few examples, and then I'll show you there are a lot of ways to prove identities. Right. So, of course, like I said, the more traditional way is we go from the more complicated sign to the simpler sign. But now I'll show you an alternative way to do that. So before to do that, notice that what I'm about to do now is not a proof. So let's say we have secant theta minus cosine theta over sine. Once again, what I'm doing now is not a proof. Now, let's try to simplify the problem, right? Assume this is right. Cross multiply because after all, we don't want to deal with fraction. So tangent and sine, swap sine times tangent. So that's what we get when we cross multiply, right? And then next, write everything in terms of sine, cosine. Secant is 1 over cosine, right? And then this cosine is good. So I write everything in terms of sine and cosine. Tangent is sine over cosine. So remember those 4 identities that I circle. So with those 4, we can write everything in terms of sine, cosine. So we have this. Now, we have a fraction. Again, the way to do this is multiply by everything by cosine. So if we do that, we have cosine times 1 over cosine. That cancel out, give us 1. Cosine times cosine is cosine square. Cosine cancel with cosine, give us sine square. Now, of course, if you did not recognize this, this is deduced from Pythagorean identity. So we move the cosine to the other side. Step 1 equal to cosine square plus sine square. So that is where we add cosine square on both sides. That's what we have. So, of course, we know this is true, right? So that should be true because all of these are equivalent operation. Now, like I said, this is not a proof because when we try to prove something, we don't assume that to be true, right? So this is given. We try to prove that. So this may or may not be true. So we cannot start with that. However, we can start with something that is true. So if we want to, we can start from here and write it backward. In that case, this is perfectly a proof. So I will write this in the reverse order. By the way, I will divide a page into two columns. One proof I do using the method I'm doing here, like working backward. And then the other method is more traditional way, where I go from one side to the other. So I'm going to do it two ways, two different ways. The first one, because I'm going to write this in reverse. First, we know for sure 1 is equal to cosine square plus sine square, because that is the Pythagorean identity. It is true. I can subtract cosine on the other side, because we can subtract the same thing on both sides. So subtract cosine square on both sides. That's what we have. And then next, what do we write? Oh, if we multiply everything by cosine, the reverse of that is divide cosine by both sides. So we multiply both sides by 1 over cosine. So pretty much, instead of multiplying, we divide. Divide is multiply reciprocal. And then we multiply across 1 over cosine times. That is going to be 1 over cosine. Cosine square divided by cosine is cosine. And then we multiply. That gives us sine square times 1 over cosine. Okay, so of course reverse process, that's what we have. Next, what we write at the sine square here, we can split as sine and then sine. Sine times sine is sine square, right? And then cosine. Finally, 1 over cosine secant. And sine over cosine tangent. So we go to this step. And finally, cross multiply. But the reverse of that is, if we want to get this side to be tangent, all we need to do is divide by sine on both sides. And then you cancel. We have secant minus cosine over sine equal to tangent, which is that. So that's certainly proof. Of course, I should write that statement again, but I'm running out of space. Here we just say secant minus cosine over sine equal to tangent. Of course, that's one way to prove it. Now, another way to prove this is more elegant. We work from the left one side to the other side. The more complicated side to the other side. So this is one way to do this. We'll do the other way, let's say alternative. This is the traditional proof, the traditional way. So we start with the more complicated side. In this case, the left-hand side. Secant minus cosine over sine. Alright. Now, the first thing is also, I do the same thing. Write everything in terms of sine and cosine. So that involves the secant is 1 over cosine minus cosine over sine. Right, secant is 1 over cosine. That's the only thing I don't here. So the secant go to 1 over cosine. Now, to simplify this fraction, I will multiply top and bottom by cosine, because cosine and cosine will cancel out. So next step is one over cosine minus cosine. I will multiply top and bottom by cosine. Because when do that, cosine here cancel out. So when we do that, we will get cosine cancel with cosine is 1. And cosine times cosine is cosine square. The bottom is sine times cosine. Right. And the nice thing about we change everything from sine, everything to sine cosine, is that if we see cosine square or sine square, more often than not, we use Pythagorean identity. So here we have the cosine square. So we might most likely we need the Pythagorean identity. So the Pythagorean identity is sine square plus cosine square is equal to 1. But here we have 1 minus cosine square. So in that case, if we want 1 minus cosine square, we just subtract cosine square on both sides. So subtract cosine square on both sides, we have sine square equal to 1 minus cosine square. Right, subtract cosine square on both sides. And we will substitute into here. So continue. From there we have 1 minus cosine square, which is sine square on the top. The bottom is sine and cosine. And then sine square cancel with sine. Yeah. So sine square, sine times sine. That cancel out. We have 1 sine over cosine. And of course that is tangent. And we say equal to the right hand side. So this is a complete proof. Usually we go from one side to the other. And that is the traditional way to do things. Yeah. And so that when we do the cross multiply, I just get the idea of how it works and manipulate. So of course you can do this or you can do that. Right, now same thing. This I'll try to simplify the expression and try to get to something that we know. Right, so cosecant tangent over secant minus cosine. Right, first thing, to simplify expression, I will cross multiply. So we have cosecant times secant minus cosine equal to tangent. Right, next, write everything in terms of sine, cosine. Cosecant is 1 over sine. Secant is 1 over cosine. And tangent is sine over cosine. Yeah, just write everything in terms of sine, cosine. Now, multiply it all out. That gives us 1 over sine times cosine. And multiply that, gives us cosine over sine. And here we have sine over cosine. Right, now to simplify this fraction, I will multiply by the common denominator of sine times cosine. Multiply that out, we have 1 minus sine cosine cancel out. Sine cancel with sine, we have cosine square. And cosine cancel cosine, we have sine square. As you see, more often than not, when we have the cosine square, sine square, that is the Pythagorean identity. So So indeed we have something that is true. Right. So once again, this is not a proof. The proof, we don't know if it is true or not. We cannot assume. We cannot work the problem from something that is not true. However, as mentioned before, if we write this in reverse, that will be a proof. So once again, I will write everything in reverse. Try to write small because this takes a lot of space. 1 equal to sine square plus cosine square. Right, so that everybody knows is true. Now we can, instead of add cosine square, we do that reverse. To go to this step, we subtract cosine square on both sides. So 1 minus cosine square is equal to sine square. Right, write that in reverse. The next step is divide everything by sine and cosine. So instead of multiply, we will divide by sine cosine. So we write the problem in reverse. So when we do that, we should have this step. Minus cosine over sine equal to sine over cosine. Right. I just write this step, but you can verify when we multiply that out. That's certainly the case. When we multiply this and this, the cosine cancel with the cosine. So the top is 1 cosine at the top and 1 sine at the bottom. And here the sine cancel with the sine. On the top is sine, the bottom is cosine. Right, so that's what we have. Right. Now the right hand side is tangent, which is easy. Now what do we do with the left hand side? On the left hand side, we'll factor out sine at the bottom. So we have 1 over sine as a common factor. We'll factor that out. We have 1 over cosine left. And then cosine. And then sine over cosine. Of course, that 1 over sine is cosecant. And then that gives us 1 over cosine secant minus cosine. And sine over cosine tangent. So once again, we write things in reverse. And finally, to get back to this cosecant, we will divide secant and cosine on the other side. Right, so that certainly works. Right, so this simplify the problem. The way we simplify is if there's a quotient or try to eliminate fraction is the most common step here. Like if we have that cross multiply eliminate fraction and then put everything in sine cosine, we have that multiply by the least common denominator to eliminate fraction. Right, so cross multiply by the least common denominator, those are the common things. And then once we simplify the problem to something that is true, we just work the problem backward and we have the proof. Right, now I'll do this more traditionally. I start with the more complicated side and then simplify that to something simplify that to the other side. So we start from the right hand side because that is more complicated. since we only have one sign, we cannot really do anything, cannot cross multiply because we only have one sign. So the first step I do is we write everything in terms of sine, cosine. Secant is 1 over cosine. Right? So write everything in terms of sine, cosine. The next step is to eliminate the complex fraction. If I multiply a cosine on the top and bottom, so we're trying to eliminate a cosine at the bottom here. So 1 over cosine minus cosine. Now we multiply everything by cosine. Cosine times cosine cancel out. And then we just have sine on the top, right? At the bottom, cosine times cosine cancel out, we have 1. And then cosine times cosine is cosine square. As mentioned before, more often than not, when we have the cosine square or sine square, that is Pythagorean theorem. And this is exactly what we have earlier. 1 minus cosine square is equal to sine square. Now, sine square meaning sine times sine, so we can cancel one of them at the top. Because if that's not a symbol as it looked, we can write sine, and then the sine square here actually meaning sine square. We cancel that. We have 1 over sine, which is cosecant. And plus that is what we have on the left hand side. So that certainly works too. Right? Just work more complicated sign, go with something that we get. Yeah, I said you can move like this or like this. This when we look at this, even though it's not wrong, but kind of a little counterintuitive, because exactly that's the way we do that. We do write the problem backwards, so that kind of awkward, but that certainly works. Right. Next, I'll try to prove this. Right. And the question is, which one is more simplifying? So, yeah, that might be a problem when we have both sides are equally complicated and we don't know where we start. So, cotangent is cosine over sine. Yeah, we don't have any fraction to eliminate, so just write everything in terms of cosine and sine. And then cosine square, cosine over sine square. And then cotangent square is cosine square. You know what? Just simplify. The 4th power here meaning that. Okay, let's write that, but more carefully this time. To the 4th. Cosine over sine square, cosine over sine square. Cosecant is 1 over sine square. So we do that. We will have cosine to the 4th power, sine to the 4th power, cosine square, sine square, cosine square, sine square, sine square. Right, sine square times sine square, that to the 4th. Don't forget the x. 4th power, sine to the 4th, cosine square, sine square, and then cosine square, sine to the 4th power. Right. Sine times sine, sine square times sine square, sine to the 4th. Now to simplify this, of course, we'll multiply by sine to the 4th power. Right? Multiply everything by sine to the 4th power. That will cancel all the denominators. Right. Sine square cancel out. We have cosine to the 4th power. And then sine square cancel with sine square. We still have sine square left. Sine to the 4th and sine square cancel 2 of them. We still have 2 left. And this, the whole thing cancel. Right, next. Yeah, of course, we have the cosine square and sine square definitely without identity. But it would be easier if we notice that both of them have cosine. In particular, if we can factor out the lesser degree, will be cosine square. Then we have cosine square left, plus sine square. And of course that equal to 1. So that is true, cosine square equal to cosine square. So that is true. Right? So if we want to prove, try this in reverse. That is the proof. So let's try that. So first we start with something that is true because anything is equal to itself. Okay, no argument there. Next, we can just multiply by 1. Nothing wrong there because cosine square plus sine square is 1 and anything multiplied by 1 is itself. And now we multiply it out. Give us cosine to the 4th power. Plus cosine square times sine square. And then cosine square. And finally, so where are we? Oh, we are at this step. Next, to get to this step, we divide everything by both sides by sine of sine to the 4th power. So we divide everything by sine to the 4th. Power. Right. Now cosine divided by sine to the 4th, I will group those together. And then the sine square and sine to the 4th cancel out. We just have cosine square, sine to the 4th. And then we have cosine square, sine to the 4th. Of course, we cannot simplify anything on this side. But what we can do is, we can write sine to the 4th is sine square times sine square, right? Those two multiply together, sine to the 4th. And then we just need to put 1 on top to hold the fraction. So that's we have a fraction. And finally, cosine over sine is cotangent to the 4th power. cosine over sine is cotangent once again, but this to the second power. Cosine square over sine square, that cotangent square, and 1 over sine square is cosecant square. Yeah, so if we write this in reverse, we have the proof. Now, if we have to prove this, so which one is more complicated? And then we just, actually it doesn't matter, but I just go from left to right here. I think the left side is more complicated, that we can simplify to here. Right, so I start from the left hand side, is cotangent plus cotangent square. Now cotangent is cosine over sine. That is cosine, sorry, over sine. Yeah, so write everything in terms of sine, cosine. Next, I'll do the common denominator of sine square, sine to the fourth. So in that case, we multiply sine square on the top. And sine to the fourth power. Cosine square times sine square. Right. Now put them together. By together, I mean common denominator. And then we have cosine to the fourth power. Here we can factor out the cosine square. When we factor out cosine square, we have a cosine square left plus sine square. So to see, most of the technique that we use here is just involving multiply by the common denominator, or sometimes cross multiply, to try to simplify things. But the starting place is where we multiply by the starting step is to write everything in terms of sine, cosine, right? So they have cosine square or factor. So factor, multiply common denominator, try to simplify the problem. Those are the common technique. But I would try to everything from sine, everything to sine, cosine, just too easy to work with. And then we know exactly what we go to. Like when we have cosine square and sine square, that definitely Pythagorean identities, that is equal to 1. So here we just have cosine square over sine to the fourth. Now we can split sine to the fourth as sine square times sine square. Then we have cosine square on the top. Then we can put 1 on the top. Cosine square over sine square is cotangent square. 1 over sine square is cosecant square. So we have cotangent square. And then cosecant square. Of course, that is the right hand side. So that's how we prove it. Yeah. Either this way or that. Yeah. This is more traditional way where we work with more complicated sign than simplify. Right. That certainly works. Right. Next. Now this is what when we see a problem like this, and then we say, which side is more complicated and where do we work with? Now, this is a perfect example of trying to simplify the problem and then work everything from reverse. In that case, that would be a lot easier. Now, let's just cross multiply here, right? Because that's the simplest way to simplify things. So that gives us cosine square equal to 1 minus sine times 1 plus cosine, 1 plus sine, sorry. So I have cosine square 1 times 1, I multiply it out, 1 times 1 plus sine minus sine and minus sine square. Sine cancel out. So cosine square equal to 1 minus sine square. Okay, what did I say, right? Most of the time when we see cosine square and sine square, that is without identity, so I will add sine on both sides. And we have cosine square plus sine square equal to 1. And the proof, of course, just need to write this in reverse. Even though it looks counterintuitive, but it certainly works. Because sometimes to go from one side to the other is kind of difficult. I will write this in reverse and I'll have the proof. So we start with without identity, so everybody knows it is true, right? And then instead of add sine square on both sides, I can subtract sine square on both sides. Now, the part where I say it's not counterintuitive, this is counterintuitive, is that from this step to this step is a bit counterintuitive, but it's still true though. So what we do is, instead of simplifying, we will add and subtract the same thing. Counterintuitive, but it's certainly true. Then we can factor out 1 plus sine factor by group the first two and then the last two. 1 plus sine x and then both of them has the minus in common and the sine x in common. So when I factor that out, we have 1 left. Factor the negative sign, we still have 1 sine left. Now both of them have 1 plus sine. Factor it out. That is a common factor. Factor it out. And then we have 1 minus sine x. And then we will divide both sides by something to get back to this. So to get back to this, we don't have the 1 plus cosine, so I will divide 1 plus cosine on both sides. 1 plus sine, I mean. If that's simplified, then we have 1 minus sine on the top. We need the cosine at the bottom as well. So we do that. 1 plus sine and cosine. So cancel that. We have 1 minus sine over cosine. And then a cosine cancel with that. We have 1 cosine on the top. 1 plus sine at the bottom. That certainly works. Right, so this is a proof. Like I said, in this problem, every problem I prove two different ways. One is to work things in reverse, and the other way is work from one side to the other. Now, this one I have to work from one side to the other. Right. So how good we do it? So because that is one way to do it, this is the other way. So let me ask you this: which one is more complicated? Well, I would say this one is more complicated because the denominator has two terms. So I'll go from the left hand side here. Because if we have to multiply something or divide by something, top and bottom, it has one term, it will be a lot easier to simplify. Right, now, we have to somehow get to this, meaning that we're going to have cosine at the bottom. Of course, we can multiply cosine at the bottom too, if we want to. We cannot just do that. So if we multiply cosine at the bottom, that certainly works, right? But, or we can multiply 1 minus sine on the top. So, there's two ways to do this, either, because we're trying to get to this one, so either we multiply cosine top and bottom, or we multiply 1 minus sine top and bottom. We hope that this will stay, so we have 1 minus sine, and we hope that this will cancel out somehow. Try to get the 1 minus sine x on the top. We try to keep it and try to get rid of the 1 minus sine at the bottom. Right? So, once again, I multiply 1 minus sine on the top with hope that I can keep that term at the end. So the answer will look like this. Or if you multiply cosine top and bottom, perfectly fine. I'm going to hope that the cosine will stay at the bottom. But this time I multiply that, and I hope the 1 minus sine will stay. So that's why on the top I do not multiply it out, because the answer has 1 minus sine x. I hope that will stay. I hope it will stay as 1 minus sine x. I hope the cosine here will cancel out. Right. So I want that to stay on the top. So just keep it like that. Don't mess with it. Now the bottom, I'll try to get rid of this. So how about multiply it out? 1 times 1. 1 times sine x minus sine x. Sine x times 1 plus sine x. And minus sine square. Right. We see that middle term cancel out. So the top, once again, stay intact. The bottom, 1 minus sine square. As mentioned many times, more often than not, when we see sine square and cosine square, that is the Pythagorean identities. Cosine square plus sine square equal to 1. So now we need 1 minus sine square, so I will minus sine square on both sides. That gives us cosine square equal to 1 minus sine square. And I can substitute that into the denominator here. One minus sine square is cosine square. Cosine square cancel cosine. So one of them at the bottom. So we have 1 minus sine x over cosine of x. And that is the right hand side. Right. So that certainly works. So this is another way to prove this. And the point here is when both sides are equally complicated, of course we just have to pick one side and go to the other. So we kind of have to hope that we get to the right hand side, right? So in order to do that, we'll just multiply something, because the top somehow need to have 1 minus sine x on the top. So I multiply that top and bottom and hope one of them will stay on the top and somehow cancel at the bottom. And indeed we do. So that's what we have. Right, so that's how we prove an identity. So how we disprove it is a lot easier. Just find a counter example and that will be it. Or another way to prove identity is we try to go from one identity and then go to something that is not true. Right. So that is also the way to do that. So we assume that it is true. By the way, we prove that this is not an identity, meaning that it is not true. So the way we do that is assuming that it is true. Right. If this is true, then the square here we can multiply by itself. Multiply by itself. The right hand side still stay the same. Don't do anything with that. Not until we have what we have on the right, the left hand side. So multiply our sine times sine, sine square, sine minus sine cosine, and minus sine cosine, minus cosine, that plus cosine square. On the right hand side we have sine square minus cosine square. Right. Can cancel the sine square on both sides. Those two are like terms that make two of them. This is cosine square. Right. Of course, we can move things around. So I can move the cosine square to the other side. That gives us negative 2 sine x, cosine x. Cosine square cancel out. And the other side is negative 2 cosine square x. Now, both of them have negative 2 on both sides, so I can divide by negative 2 on both sides. Both of them have cosine on both sides, so we divide by cosine. So cancel cosine, cancel negative 2, so we have sine. And cancel out negative 2. Cosine square cancel cosine, give us cosine. And of course we know this is not true. But we assume that it is true. It is equal to something not true, so the assumption is wrong. So in that case, that is not identity, so this is not true. So this is proof by contradiction. We assume that is true, but it is equivalent to something that is not. So that is not true. So this is proof by contradiction. Yeah. So most important, it's not true. Sorry. Oh, it's not an identity. Right. So By the way, if we try to prove an identity, that's why we cannot assume that. That's why cross multiply is not allowed anything. That's why this is not the proof. The proof is the problem written in reverse. Because originally we don't know if this is true or not, so we cannot manipulate from something that is not. However, if we manipulate that and we turn out something true, and we can work backward, and each of the steps are equivalent relation. So if it is true, the next one is also true, the next one also true, and we go backward, it's true. So if we want to prove, it has to be in the backward direction. Or if we want to, we can just work from one side to the other, which is more traditional proof. So I do, in this section, I do every problem in 2 different ways. So you can choose one that works. But I'll stop the section here, stop the video here. As always, thank you for watching, and see you in another video in trigonometry.